what I wanted to start with is you've often been characterized as someone with like non-traditional, kind of out there ideas, some of which have become, part of the physics canon, some of which who knows what happened.
They all became part of the physics canon. Every single one of them. I never made a mistake.
Of course. All right. Well, thanks for coming on the podcast. You're the first person who's never made a mistake.
Right.
I was curious, who do you think is your most outlandish friend?
Wait, let's come back to your previous question for a moment.
Okay.
Mm-hmm. I am very mainstream. I am not at all a alternative thinker. This is some misconception, which I don't know how it happened, but my physics has been extremely mainstream. It may have been that at the beginning of some of the ideas, people were not quite ready, but they very quickly caught on. It's just not true that I was some kind of alternative, what should we call it? I don't know what the right word is.
Yeah, some kind of radical thinker.
Not at all. Not at all. Now, I spent a lot of time thinking about, what should we call them? Conflicts of principle.
Okay.
Situations where things were not fitting together properly, and thought a lot about them, and eventually came to the conclusion that you had to change things, or that you had to break the mold a little bit. And I think that's probably where this reputation came from. But these were things that really there were no alternatives to. What was it that Sherlock Holmes said? Do you remember the quote? When you've tried all possibilities, and I forget the exact, but roughly speaking, when you've tried everything and it doesn't work, whatever remains must be the truth, no matter how outlandish or something like that.
So a little bit like Occam's razor.
Yeah, a little bit like Occam's razor. But in particular, when you've tried everything and it doesn't work, there may still be something left that you haven't tried yet because you thought it was too outlandish. Well, you got to try it. Mm-hmm. And I think that probably is the source of some of this mythology about me as a radical. But I am the most conservative physicist imaginable.
Okay, so what's an example then of a friend who is more outlandish, more radical than you?
Freeman Dyson. I can't exactly call him a friend, but I know him a little bit. Mm-hmm. He is what you might call a contrarian. He enjoys running against the grain, and he sometimes says some brilliant and smart things. Mm-hmm. Like all contrarians, he's got a very large probability of being wrong.
And he's willing to.
My friend Herrada Tuft, I don't know if you know his name. He's a very famous physicist. He's also a bit of a contrarian. He's far more out there than I've ever been. Was Dick Feynman a contrarian? No. He was about as mainstream as you can be. But also had his own very special scientific personality. And I suspect that's also true of me, that my way of thinking, my way of doing things is probably different than most people. And so, it did lead to this view of me as a contrarian, as a radical, but it was absolutely wrong.
And do you see physics like kind of birthing more contrarians in the modern paradigm where experiments are so expensive to, kind of execute at this point? Or do they have to be kind of more mainstream to get things done?
Well, unfortunately, I think you have to be really mainstream. Sometimes I think too much.
Okay.
Sometimes I think too much. By mainstream now, I mean people are often trained within a framework which is fairly tight and rigid. And I sometimes think maybe a little more free thinking out there might be useful. Free thinking, but that doesneen mean being a contrarian. A contrarian is somebody who is contrary just for the sake of being contrary.
Yeah.
Right?
Well, because I mean, I read your Wikipedia page, listened to interviews with you, and I heard about you being a plumber, working with your father. Yeah, which is true.
Okay.
But it's like, and now here we are at Stanford,
right.
and you're kind of like of the industry, right? You're here.
Yeah, it took me a long time to feel part of the, to not feel an outsider.
Yeah.
My background was a little bit strange so it took me a long time to not feel like an outsider. And then all of a sudden I found out I was the ultimate insider.
And how do you deal with that? It's hard.
I just ignore it.
Okay.
I do my thing.
Yeah, fair enough.
I'm interested in the physics problem. I'm not going to let it go. I spend most of my time thinking about it and not agonizing about other things.
Then where do you go to think of new ideas? Because that's something that...
You mean, do I go to the bathroom or do I take a shower? Or
yeah, do you take a shower? No, I'm kind of curious where your ideas have come from over the course of your career.
They almost always came from some sense that things were not fitting together properly. What I call a conflict of principle or a paradox. One of the early things that I worked on was what's called quark confinement. Why don't quarks come out of particles and appear in the laboratory? Okay. They seem to exist. They seem to be part of the proton and neutron and so forth, and they seem to be stuck inside and never come out. All right, and that appeared to be a paradox, because from all that we knew about the subject is quantum field theory, the subject that governs particle physics, from all that we thought we knew, any kind of particle that exists should be possible to kick it out and observe it directly in the laboratory. So there was a paradox there. They seem to exist, and yet they seem not to exist. Something was wrong. And that's the kind of thing that captures me and gets me going. And I don't want to let it go until I feel I understand it.
So someone from Twitter asked a question related to this. Their name's Claudio, and they asked, do you think the graviton can be experimentally found? So similar...
Well, of course, there's a sense in which it's already been, but this is, I think I know what they mean, but gravitons or photons or some large class of particles, when they're in sufficient abundance, just behave like wave fields. So the electromagnetic field is a collection of photons. But that doesn't mean you can detect them as individual photons easily. Radio waves, for example, would be very, very difficult to detect as individual photons. All right, we've seen gravitational waves. That means we've seen large numbers of gravitons.
Yep.
I mean, I don't know how many, just zillions and zillions and zillions of them. I think what the person was asking about is the possibility of seeing them individually. That seems very, very hard. I don't see any easy route to that. And in fact, I guess I don't see any route to it at all. But ultimately, I think it's a technological problem.
Okay.
If you could build an accelerator as big as the galaxy and so forth and so on, and harness 100,000 stars to take all of the energy that they produce and run the accelerator with it, you could make gravitons. So it's a technological problem.
Okay. So it's a little bit like the space LIGO.
The space LIGO. Wait, the space LIGO is a trivial technology. It'll be easy.
Really?
What is the space LIGO? What is the
LIGO in space?
Yeah.
That's trivial?
By comparison.
By comparison.
No,
okay.
no. I mean, I don't want to insult my friends. No. It's trivial in the sense that in principle, we can do it. We will do it. And it probably doesn't involve any technological hurdles which are insurmountable. Building a machine that could produce gravitons, at least for the next million years, is going to be insurmountable.
Oh, wow.
No,
okay.
It's not. I think it's not going to be done.
Right.
On the other hand, maybe I'm wrong.
So let's go to some of your other ideas. So, you're credited as one of the creators of string theory,
which is extremely mainstream. Which
is super mainstream. Yeah,
but okay. It wasn't when we started it.
Correct. So well, that's where the idea. Right.
So that's where the idea of me as a radical came from. But now it's mainstream.
Where did the idea come from?
Oh, well, the idea came from asking about the structure of particles which are known as hadrons. These are protons, neutrons, mesons. They're common things that make up the nucleus. And there was a lot of work, experimental as well as theoretical, which showed that these particles were not elementary particles, that they were composites of some sort. You could spin them. You can't take a point and spin a point. The point is too small to, what does it mean to rotate a point?
Okay.
Okay. Whatever protons and neutrons were, you could spin them up. You could increase their angular momentum. They seem to be capable of being vibrated and excited in all sorts of ways. There was some mathematical work. It was very mathematical and didn't have to do with strings, but which caught some of the properties of these hadrons. And I got interested in it and just looked at some of the formulas and said, ooh, those formulas are interesting. I wonder what they mean. Look at it a little more. And I said, oh, there's something vibrating. There's some kind of concept of vibration going on. And it was just a matter of thinking about it for a few weeks and saying, oh, the strings, they're elastic strings.
And with each of these, like, were you deeply knowledgeable in the field before or this? Okay.
No, I was deeply knowledgeable about quantum mechanics.
Okay.
At least, well, was I deeply knowledgeable? Even that, I think I was. But yeah, I had a very, very good education. It was self-education about quantum mechanics, about classical mechanics. I did not have much of an education about particle physics. But it was unnecessary. Somebody showed me a formula, and it was a mathematical formula. I knew what a proton was. I knew what a neutron was. I knew that if you collided them, stuff come out of them. And I also knew that that they had these properties of being capable of being excited and spun up and so forth. So I did know that. But that was easy. I mean, you know, I just told you, and you now know it too. Okay? They showed me a formula. And the mathematical formula had some pieces in it that I recognized. I'd seen it before. I'd seen it in the context of basically elementary quantum mechanics. I'd seen it before, and I looked at it. And at first I thought, oh, this thing is just a pair of particles on the ends of a spring. Meaning to say the mathematics of it was the mathematics of what's called a harmonic oscillator. Okay. But I looked at it a little more and a little more and a little more, and eventually I realized that the formula was representing the interaction of particles which themselves were string-like. String-like meaning elastic threads, let's call them. And so I worked it out and published it, and that was the story.
And then in the Cornell lectures from 2014 or something like that?
Oh, the messenger lectures.
The messenger lectures.
Yeah.
You kind of like offhandedly said that despite being one of the creators of the string theory, you weren't the biggest believer in the world right now.
Oh, okay. I probably did say that, and what I had in mind was something like this. I do believe in string theory in the following sense. It's a mathematical theory, it's a consistent theory, and it contains both quantum mechanics and gravity. That makes it a very, very valuable laboratory for trying out ideas. It in itself doesn't mean it is the theory of the real world. Okay? My guess is the theory of the real world may have things to do with string theory, but it's not string theory in its formal, rigorous mathematical sense. We know that. We know that. We know that the formal, by formal I mean mathematically rigorous structure that string theory became. It became a mathematical structure of great rigor and consistency that it in itself, as it is, cannot describe the real world of particles. It has to be modified. It has to be generalized. It has to be put in a slightly bigger context. So the exact thing which I call string theory, which is this mathematical structure, is not going to be able by itself to describe particles. Will what does correctly describe particles be a small modification of it or a big modification? And that's what I don't know.
Okay.
But I do know the value of it as a laboratory for investigating quantum mechanics and gravity. And that's remarkable.
Okay. Because the question that I've been wondering, and it's sort of straightforward, but why does there have to be a grand unified theory?
Well, there has to be. Why does there have to be?
Or do people want it?
We don't. I don't know what people think. I know what I think.
Okay.
It's not tolerable to have inconsistencies in the theory of nature, where one piece of the theory says one thing, another piece of the theory says another thing, and they're saying inconsistent things. They have to be made consistent. Right. At the present time, we're in the business of trying to put together a consistent framework for the combination of gravity and quantum mechanics. Mm-hmm. Elementary particles, there are inconsistencies in what we know about elementary particles. We're trying to put those together. When we put them together and make a consistent story out of all of this, we'll call that a grand unified theory. That's it. Mm-hmm. And it's it's intolerable not to have a consistent story. You get different answers by doing different versions of it. That can't stand. So that's my answer to it.
Okay. So when you look at physics as it stands right now, mm-hmm. where do you see the cracks that you want to be focused? Is that like the most important thing you could possibly be working on right now?
Which?
A grand unified theory. In other words,
I don't think of it that way. At the moment, people like myself, John Preskill, Juan Maldacena, wonderful and great physicists, have gotten focused on the connection between quantum mechanics and gravity. Mm-hmm. For many years, it was thought that quantum mechanics and gravity simply don't fit together. For a variety of reasons, including things that Stephen Hawking had said, mm-hmm. which were brilliant. I don't think correct, but brilliant anyway. It really looked like there was an inconsistency between quantum mechanics and gravity. Quantum mechanics governs all other parts of nature. But of course, gravity also covers a large part of nature. And to have inconsistent theories is, as I said, intolerable. Mm-hmm. So the puzzle of putting together quantum mechanics and gravity is the one which is front and center for me, and I think front and center for theoretical physics right now. Mm-hmm. There are also, conflicts. There are conflicts in our understanding of elementary particles. We don't understand how they can behave certain ways that they do behave. One of the problems, it's just a name, but it's called the gauge hierarchy problem. It's an apparent almost inconsistency in the, let's call it the standard model of particle physics. There are other questions about how it does fit together with gravity. Mm-hmm. We made great progress in understanding elementary particles for a long time, and it was always progress that went hand in hand with experimental developments, big accelerators and so forth. We seem to have run out of new experimental data, even though there was a big experimental project, the LHC at CERN, whatever that is, a great big machine that produces particles and collides them. Mm-hmm. And I would say, I don't want to use the word disappointingly. Well, I will anyway. Disappointingly, it simply didn't give any new information. And so particle physics has run into what I suspect is a temporary brick wall. It's been basically since the early 1980s that it hasn't changed. And so I don't see at the present time for me much profit in pursuing it. Gravity and quantum mechanics are what fascinate me.
Well, what are the other large unanswered questions that people are pursuing at this point? Like, because clearly it's not just you working on this, right?
No, I think other things. Mm-hmm. Well, in the context of, there are huge problems in cosmology. in all of this, cosmology is about quantum mechanics and gravity.
Mm-hmm.
Early cosmology, so-called inflationary theory, is about how quantum fluctuations imprinted themselves on the universe and led to the things, galaxies, planets, and so forth. So quantum mechanics and gravity are the foundations of cosmology, but we don't understand how they fit together at all. Not particularly in the cosmological context. We really just don't understand how they fit together. The dark energy, the thing that's called dark energy, is a puzzle. It's not the puzzle of why is there dark energy. It's the puzzle of why isn't there a lot more of it. The dark energy is a tiny, tiny, minuscule fraction of what it could be. Why is it so small? 10 to the minus 120 of what the natural expectation for it would be. So for many years, people thought there was no dark energy.
Mm-hmm.
We call it the cosmological constant, but it's the same thing as what people call dark energy.
Okay.
We have no idea. So originally we thought it wasn't there at all. It's also, Einstein invented the cosmological constant and then said it was his worst mistake because it doesn't seem to be there.
Okay.
Well, it was there, but it was there at a level which was so minute that it took until the 1990s to discover any evidence for it.
How is it measured?
It's measured astronomically and by modern observational cosmology.
Okay.
Counting galaxy counts and all kinds of things, quasar counts, all sorts of stuff.
Okay.
But the main point is, in the end, it turned out that it was there, this dark energy, but it was there at such a small, incredibly small value that it took all that time to get any evidence for. And we don't know why it isn't bigger, more of it. And that's the puzzle. Not why is it there, but why is it not there in larger abundance?
Do you have a hypothesis?
Well, the usual hypothesis is that the usual hypothesis, the only one that I think makes any sense, which is outlandish. There's no question It's outlandish. It's not mine.
Oh, are you jealous?
No, it's not mine, but I think it's the only thing that does at the moment seem to make any sense, is to say the universe is extremely big, much bigger than we can see, and varied. Varied means it has properties which are different from place to place. That's a good theoretical idea. It does fit together with the equations and so forth, that the universe is vastly bigger than the part we can see, and that as you scan over the whole thing, you'll find places where the constants of nature are one thing, other places where the constants of nature are another thing. Mm-hmm. Some places where this cosmological constant is more or less normal, which means much, much bigger than it is here in our neighborhood. Some places where it might even be smaller. But then the question becomes, in what kinds of environments can we exist and even ask the questions? My friend Steve Weinberg, in around 1987, made an argument that if the cosmological constant were any bigger than a certain magnitude, that galaxies could not have formed. And if galaxies couldn't form, stars can't form, planets can't form, and we can't be here. So he said, all right, the answer is the universe is very big and varied, and we are where we can be. That's all. We're just where we can be. That's called the anthropic principle, and it's a widely hated idea among physicists.
Definitely among scientists.
It's a widely hated idea, but it just might be right.
So I was listening to a radio interview with you, and you said, similar to this, that there was a discovery that there are relatively few ways of organizing matter than we thought there would be.
And what the hell I was talking about?
That's a good question. But my question is, could you explain? Because you said there are relatively few ways that don't turn into black holes.
Oh. I don't remember exactly what I was talking about.
Okay.
But here is what I can tell you. Almost all the matter or almost all the information in the universe is in the form of black holes. If you take some matter and just generically populate the world with matter, you will find in a very quick amount of time that it's mostly all black holes. Our world is mostly all black holes. It really is, in the sense that the information stored in matter is at least, let me think, I think about 10 to the 10th, a factor of 10 to the 10th more information stored in black holes than in anything else. Even though black holes seem very rare in the universe, they contain almost everything.
Can you define information just for people?
Yeah, it's what's in a computer.
Bits?
It's bits.
Yeah, okay.
Bits. The bits, we call them qubits because they're quantum bits, but yeah, bits. And the bits which determine, here's what we might say. We take the universe as it is. We can run it forward in time, and that'll tell us what it will be. We can also try to run it backward in time to find out what it was like in the beginning. Right? In order to do that, you have to have every single bit accounted for. You try to run things backward, you'll make mistakes very quickly unless you've accounted for everything. So the question is, how many bits of information do you need in order to run backward and find out what the world was like in the beginning? And that number of bits is about 10 to the 10th times bigger than all the known bits in ordinary material in the universe. Protons, neutrons, electrons, and so forth. Where is it hiding? We now know that it's hiding in black holes.
Gotcha. Okay. So I briefly encountered this through the holographic principle that you worked on.
Yeah.
And one question that I couldn't fully wrap my head around.
There's another example of something which was considered a little bit radical at first, a little bit nuts, but of course it's now extremely mainstream.
Yeah.
Very mainstream.
But I would push back a little bit,
Okay, go ahead.
Well, like anything that's fringe that becomes popular, you can say is mainstream, but it was fringe in the beginning.
No, it's mainstream in the sense, well, it wasn't fringe in the beginning. People just didn't recognize how essential it was to the logic. It took a little while. It took a little while for people to realize, yes, this was the only way it could be. It wasn't just that it became popular. This is not a popularity contest. Physics is not a popularity contest. For brief periods of time, sometimes things become popular, but they don't last if they're just popular. They last if they have value, explanatory value, predictive value, and the value of leading to a consistent framework. In that sense, the holographic principle is now completely mainstream. And why is it mainstream? It's mainstream for the reasons that I thought it had to be correct. It just had to be correct. It could not be correct.
It worked out. So can you give a brief explanation? Because this was a hard one.
Yeah, well, it has to do with black holes. It had to do with black holes and the information law, which it had to do with this discussion about information being lost in black holes, which was Stephen Hawking's very, very brilliant insight, even though I think he got the final answer wrong. It was a very brilliant insight to ask what happens to the information that goes into black holes. Is it lost? Is it lost to the universe? If it's lost, that would be a major change in physics in which in ordinary physics information is never lost. Now, Stephen also said that black holes evaporate. Well, a natural answer might be that that the information comes out in the evaporation. But it can't come out in the evaporation if it fell into the black hole because nothing can get out of a black hole. Okay, so there was my favorite kind of situation, a clash of principles. The answer turned out to be in this holographic idea that let me say it in a way which is not exactly correct, but as close as I can get without writing a bunch of equations on the blackboard. the information that falls into a black hole can be thought of as both falling into the black hole and also getting stuck on its horizons. Two versions of it. Almost as though the information was Xeroxed at the horizon of the black hole, and one half of it sent in and the other half stored on the horizon. Now, the real statement was more like saying the stuff on the horizon is a kind of hologram of the stuff that falls in. So it's really only one thing, but represented in two different ways. And then once you said that the stuff that falls into the black hole can be thought of as a hologram that never does fall through the horizon, then you can imagine that when the black hole evaporates, this hologram evaporates with it and it carries off the information. Now that's
yeah. So this was the challenging part for it. So
that's very challenging, right? And I'm not sure that I can. I think if you really, really wanted to know, and you were willing to spend 3 or 4 days talking about it with me, I could probably reduce it to something which was both correct and comprehensible, but not in 15 minutes.
Yeah, fair.
Not in 15 minutes. It's just the way it is. And
so,
okay, but the point was that black hole horizons are behaving like holograms of anything that falls into the black hole. But then, when we're thinking about it further, we realized that the whole world could be in a black hole. You can't tell that it's not in a black hole.
Okay.
Right. In particular, the entire universe has a horizon out at very large distances, which is very much like a black hole horizon. And we're kind of inside it. So that leads to the conclusion that we here in the interior must have another representation as a hologram out at the boundary of the universe. Now, this was a strange idea. This certainly was a strange idea. I felt driven to it because I could see no way other than that to, incidentally, it wasn't just me, it was also Gerard de Tuft who put this idea forward. And it was a little bit out there. It certainly was out there. It didn't come in from the cold, shall we say, until the work of Juan Maldacena, who made a really rigorous, beautiful version of it, which now everybody believes. The mathematics of it was, it was a string theoretic construction, where Juan showed how, at least in certain setups, the universe would have to be regarded as a hologram. A hologram, saying it's a hologram is a bit of an analogy.
Yeah.
But that it would be represented as information stored on the surface, on the outer surface of the world, rather than in 3 dimensions as we normally think about it.
Inside, yeah.
Yeah, that Juan really nailed that with such mathematical precision that it just became part of our standard. It became a tool.
Okay.
That's a good thing when things go from being, they often start out as very speculative. Then they become something a little bit better than speculative, conjectural. Conjectural is better than speculative. And the end process is they just become a tool of physics. Things that everybody uses all the time because it has a predictive value, a mathematical value. The holographic principle is a tool now. So yeah, it's stuck.
So why does it have to be holographic? So in other words, say it's mapped around. I'm going to have to bring this into a 3D world, right?
Yeah.
So there's a 3D sphere. Call it a black hole.
Right.
Why is it holographic versus a 2D image, for example?
It is a
mapped
2D.
Around.
It's a 2D. You mean, why can't it just be like a picture on the wall?
Yeah.
Well, a picture on the wall is 2-dimensional. It may deceive you. A clever painter can paint a painting which, when you look at it, you think you see 3-dimensional things.
But you never do.
You don't. And in particular, if you move your head around from side to side, you can't see what's behind the flower. There is nothing behind the flower. and you were just deceived into thinking there was something three-dimensional there. But how would you check it was three-dimensional? You would check it was three-dimensional by going around to the other side and see if something's there.
Mm-hmm.
Well, if you move your head around with that the picture of that plant on my wall there,
Mm-hmm.
you will not see anything behind the plant. There's just nothing there.
Mm-hmm.
It's strictly two-dimensional. On the other hand, it is possible to map a three-dimensional world onto two dimensions, but never in a way in which the two-dimensional stuff looks anything like the thing you're mapping. It will look random. It will look like a simply confused jumble of little tiny scratches. You can see that if you can get a hold of a real hologram, which a hologram does map three-dimensional space onto a two-dimensional film, and somehow look at the film through a microscope or something, you'll see that there's nothing on that film which resembles anything like the thing that it's representing.
Mm-hmm.
It's just a bunch of little tiny scratches and random noise almost. So you can't map the three dimensions to two dimensions without really making it totally discontinuous. The word is mathematically discontinuous.
Mm-hmm.
But yet it does contain the same information. That's the same thing about this holographic principle. The horizon really did store all of the stuff that fell into the black hole, but in a way which you could not easily reconstruct. It's more like a hologram than it would be like a photograph.
Mm-hmm. And how does the reconstruction happen? So say we are in a black hole.
For a real hologram, all you have to do is shine the right kind of light on it and it
Right.
will reconstruct the image. Not here. Here it would be a mathematical reconstruction. If somebody gave you the quantum state of the horizon of a black hole and you were smart enough, I assure you that nobody's smart enough, but with sufficient kind of technology of quantum computation and so forth, and if we knew the precise rules by which black holes evolve,
Mm-hmm.
we could reconstruct from the quantum state of the horizon. We could reconstruct what fell in, what's inside, and so forth.
Mm-hmm.
We could reconstruct that world that fell into the black hole. This is not something which is easy. It is far from mathematically tractable with present computers
Right.
and so forth. But in principle, it is possible.
Okay.
Right. If somebody showed you the hologram, incidentally, of just a patch of flowers or something, and just gave you the film, and didn't allow you to shine light on it, just said reconstruct from that, you'd have a hell of a time.
Yeah.
Eventually you probably could, but it would be very hard.
Mm-hmm.
Right.
And multiply that out to the universe.
And add quantum mechanics, which escalates the story hugely.
Gotcha. Slight tangent. Have you followed any of these ideas around we live in a simulation? These simulation hypotheses?
Yeah, it doesn't seem to me to add anything.
Mm-hmm.
What does that mean? Does the idea that we live in a simulation mean that there was a simulator, that somebody simulated us?
I believe so. Yeah,
I think
we live in a
implies-
computer program.
Yeah. But
based on our ideas of what
No,
it might
but I
be.
would
Yeah.
say, of course, we live in a computer program. The program is called the laws of nature, and the computer is the world. So I'd say, yeah. But then somebody would say, oh, that's not what I meant. I said, what did you mean by saying we live in a computer? I think they meant that there was a computer programmer who programmed it for some purpose.
Mm-hmm.
Do we live in a computer program that somebody programmed for a purpose? I have no idea.
Nor do you
I
spend
would
much
love
time.
to know. But, then I would ask, I'm a curious person. I would ask then, okay, if there is that guy out there, let's not give him a name, the programmer who
Right.
programmed the simulation, who programmed him?
Right.
What are the laws by which he functions? Does he satisfy the laws of quantum mechanics? He or she?
Mm-hmm.
Probably neither. It's probably a sex-free environment that
Who knows?
who knows? Yeah,
So whoever programmed them decides.
Right.
Yeah.
And then who programmed the programmer who programmed the program and so forth. It
Right.
doesn't satisfy. It just doesn't lead to any satisfying answers.
Yeah, this reminded me. I was listening to your Caltech, your Feynman lecture at TEDx, and you said something really nice, which was Feynman didn't much like philosophers philosophizing about science.
Right.
And in the context of machine learning, which your son works on, do you find yourself in the same camp? You just like back to basics about the technical aspects, or do you philosophize or let yourself philosophize?
First, let me say something about Feynman.
Okay.
Feynman claimed to dislike philosophy. He did dislike philosophy, but I'll tell you what that means in a minute. And yet he was the most philosophical of all physicists. He really was. He was a deep philosopher. When I say he didn't like philosophy, I meant he didn't like a certain style of thinking that was full of jargon, I'll use his word, baloney. Where people who didn't know what they were talking about pontificated and used fancy words like ontological, which I never knew what that meant. Right?
I know a lot of words and when you use them, but I don't know what they mean all the time.
Yeah. As a substitute for simple thinking.
Yeah.
Okay. That is what he didn't like. And yet I think in some ways, in some deep way, he was an extraordinarily philosophical person. Mm-hmm. If you read his works, I don't mean his physics works, if you read the things he wrote about the world, the ordinary world, they're very, very philosophical, but they're also incredibly simple, and they cut through all the crap. And it was the crap that he didn't like.
Okay.
Yeah. I would say the same about mathematics. He didn't like the overly fancy mathematics, but he was a very good mathematician.
Mm. And what we were talking about before we started recording, like he was also quite moral, right? In his philosophy of the world, he was affected by that. I mean, working at Los Alamos as well.
Yeah. He had he hated the fact that he had participated. He hated the fact that he had participated in the invention of nuclear weapons, and he doubly hated the fact that he had so much fun doing it.
It's fair,
right?
Yeah. Did you interact with any other people that worked on the bomb?
Hans Bethe.
Okay.
Hans Bethe was one of my thesis advisors. Yes, so I did. But I didn't talk with Hans. Hans was not, he was a friend, but he wasn't a friend in the same way that Feynman was. He wasn't a soulmate.
Okay. And that depth you talk about with Feynman, did you find that with your advisor? Did he have the same sense of grief around what he had created?
Oh, well, I can't. All right. I know the answer to that, but not from him directly.
Oh, okay.
I know from the answer from that, just because it's historical. Yes, he was very upset about the bomb. And he, as much as anybody, worked hard, very, very hard for disarmament and nuclear disarmament. Mm-hmm. Feynman did not. Feynman just said, "Okay, I'm going to do physics, and that's what I'm going to do."
Yeah.
And he didn't work. Hans did. Hans was very, very active in nuclear disarmament. So I do know that he regretted it, but I don't know it directly from him.
I'm wondering what the parallels might be today, because I think there are so many engineers working on incredibly technical things that who knows what the implications might be. Or, I mean, already are, you could say with Facebook, other things.
Yeah. On the other hand, the enormous amount of good that has come from technology, of all kinds. So I think you can't not work on it. How do you, at what point do you stop and say, this is dangerous? Well, I think it's probably built into some people curiosity, the need to explore, and they're just going to do it. Mm-hmm. It's not. I don't believe it's the physicist's job to decide what should and shouldn't be discovered. From a physicist's point of view, everything should be discovered, if possible. it is the job of politicians and other people of that ilk to make sure that things are not misused.
Mm-hmm.
The misuse of nuclear weapons was not really the scientists who built them. They were worried about the Nazis getting them. If there was misuse, there's all sorts of debate about whether nuclear weapons were misused or were they used well to end the war and all that sort of stuff. If they were misused, it wasn't the scientists. The scientists didn't want to see the bombs used. So they were given a problem, a double problem. Part number one of the problem was the Nazis are going to build it if we don't.
Mm-hmm.
And the second problem was, how do you build it?
Mm-hmm.
They had no choice. I don't believe they had any choice except to go and do it, both as scientists and as human beings. The fact that it got misused, I don't believe was the scientists themselves.
Mm-hmm.
And if anything, those people tended to be very traumatized by the fact that they had built weapons.
You said he didn't work on disarmament, but do you think any of his focuses later in life were related to, I don't know, improving the world?
I think he would have said you improve the world by discovering what the world is. I think he would have said that it's my job as a physicist. When I say my, I actually mean mine too, but I meant his.
Mm-hmm.
That it's his job to find out as much about the world as can be found out. And he was very good at it. He advanced our knowledge of the world. How it gets used is something that's not, he did not see as his responsibility.
Does that align with your personal philosophy, your reason to work
so.
on this?
I think so. Look, if I were to suddenly discover something that I knew was going to be exceedingly dangerous, I would, and I was absolutely certain that it was destructive and so forth. First of all, I don't think you can hide it.
Mm-hmm.
You can't hide it. It's going to come out.
Eventually.
It's going to come out. Right.
Okay, yeah.
So all you can do is warn. All you can do is warn people that that this is there. It will be discovered. You've got to worry about it. Well, Beta did that. I think Feynman didn't. His reaction to it was, my job on Earth is to learn about the world, and I'm going to focus on that. And I am not responsible for all the evil in the world, and I will, I can be responsible for uncovering what nature is like.
Mm-hmm. Well, because I'm just curious how you've stayed motivated and been so prolific.
Yeah,
with your career.
Well, I think I'm also a curious person. I don't mean weird. The other people can decide that. I mean that I have a sense of curiosity about the world.
Right.
And it just doesn't go away. I mean, I didn't say to myself, I'm going to continue to do physics until I'm 78 years old.
And then I'm out. Yeah.
No, I didn't plan that. I just get curious about things. And that's it. I don't have a choice.
What are you most curious about right now?
Gravity and quantum mechanics. How they fit together.
What in particular?
Whether the laws of gravity are really just the laws of quantum mechanics a little bit hidden. My guess is that almost everything we know about gravity is coming straight from quantum mechanics, and that there are equivalent rules of quantum mechanics which reflect the gravitational things. This is going to get us into technical discussion.
Let's do it.
You want to do it?
Yeah, let's do it.
No.
Yeah.
No.
I mean, if I get dropped, if some of the listeners have to drop, that's okay. But certain people will like it a lot.
Yeah, right. It's good. So one of the things that was discovered by myself and Juan Maldacena, probably more by Maldacena than myself, we wrote a paper together, is called the ER equals EPR hypothesis. Oh, this is a great story, incidentally. Let's back off for a minute. Let me tell you the story about Einstein and ER and EPR.
Okay.
ER stand for two names. Einstein and Rosen. EPR stands for three names, Einstein, Podolsky, and Rosen. In one year, 1935, after it was generally deemed that Einstein had, was basically finished as a physicist for at least something like 10 years, Einstein wrote two papers, which nobody paid too much attention to for many years. One of them was the ER paper, and it was about wormholes. It was about solutions of the Einstein field equations, which had this wormhole character where there were wormholes connecting distant regions of space. They were called Einstein-Rosen bridges. If you look up Einstein-Rosen bridges, you will find that they're bridges which connect different regions of space. A black hole in one place and a black hole in another place has a connection between them. And that was solutions of Einstein equations. The other paper that he wrote the same year was about something called entanglement. And entanglement is something that can happen to quantum systems when they get correlated, and it's a very non-local kind of thing. It's purely quantum mechanical. It does not obviously have to do with gravity. And these were two separate things. I do not believe that Einstein at all had any idea that they were connected. The Einstein-Rosen bridges and the idea of entanglement. And one of the really odd things was that, in very recent years, we found out that entanglement and Einstein-Rosen bridges are the same thing. That, in particular, an example would be if you have two black holes. Black holes have all kinds of internal structure to them. They're quantum mechanical objects.
Okay.
If the two black holes are entangled, they will have an Einstein-Rosen bridge connecting them. If the two black holes have an Einstein-Rosen bridge, they will be entangled. We found out that they are the same thing, quantum entanglement and the kind of connectivity between systems that were called Einstein-Rosen bridges. So this was a weird quirk of history that in the same year Einstein discovered both of these things. Almost certainly didn't have any inkling that they were the same. Of course, maybe he did, but I don't think so.
What did the two papers say if they ultimately became the same thing?
One paper said, there are solutions of my equations in which distant black holes are connected by wormholes.
Okay.
The shortcut between them
is entanglement.
That's about black holes. That was not about quantum mechanics.
Okay.
That was about Einstein's general theory of relativity, which is a completely classical non-quantum mechanical thing. The other thing is he was thinking about quantum mechanics and discovered this odd non-local connection that systems can have that we call entanglement. As far as I know, as I said, he didn't draw any conclusions about any relationship between these two things. That happened in 2013, long, long after Einstein had been dead for many, many years, as a consequence of the mathematical study of black holes. It was largely Juan Maldacena's discovery. I happened to be on the paper with him because we were working on something together. And that drawing out the ultimate conclusions of that, finding out what it really means, how it brings quantum mechanics together with gravity, has been the essential focus of my own thinking for at least 5 years now. Yeah. And trying to make a theory out of it, trying to build a comprehensive theory.
And what was the technical part you wanted to get to?
The technical part had to do with something called quantum complexity theory. These wormholes that connect, you might think if you have a wormhole connecting two distant places, you could jump in one and come out the other.
Yeah, that'd be great.
The problem is the wormhole grows, and it grows so fast that you can't get through it. It's as if you had a tunnel, New Jersey, New York City, the Holland Tunnel or the Lincoln Tunnel. And you go in one end of the tunnel, and of course you can come out the other end. But what if the tunnel was growing while you went in, and it was growing so fast that it grew faster than your speeding car. Well, then you can't get out the other end.
Right. Yep.
That's the way these Einstein-Rosen bridges behave.
Okay.
Okay. So the question is, what is the the quantum mechanical meaning of the growth of these wormholes? The answer appears to be that they are connected with something called complexity theory. Complexity theory is a computer science concept. It tells you how hard it is to reverse something, and the complexity of the growing Lincoln Tunnel would be a measure of how hard it would be to shorten the tunnel again so that you could get through.
Okay.
So this question of quantum complexity theory has been sort of focused on what I've been thinking about. Other people think about different things. This is a main focus of a lot of work on what's going on both here, Princeton, all over the world. And where it will go, I don't know. It's just fun to think about.
It's cool.
And they pay us to do it.
Yeah, it's not a bad gig.
Yeah.
So there was a related question from Twitter for you. So Noah asked, could quantum teleportation be used in the future as a means of intergalactic communication?
No. In order to do quantum teleportation, you cannot do quantum teleportation without at the same time sending classical information from one place to another. Classical information means, the dots and dashes, Morse code dots and dashes. You can have two entangled systems, and you can send information through the entanglement, but not without sending a code to decode the, without sending a code classically from one place to another, and that will take the amount of that will take time. So you don't speed up communication. If it would take you 100,000 years to communicate from one end of the galaxy to the other end of the galaxy in any kind of normal sense, it will take you that same 100,000 years to do quantum teleportation. So yeah, you could use quantum teleportation to teleport stuff over vast distances, but it won't be any faster. It'll be more secure.
Right.
More secure means more secret. You won't be able to crack it. But that's what quantum teleportation does for you. It gives you absolute 100% security that no classical, non-quantum mechanical protocol could ever give you. But it can't be done faster.
Okay. Good to know. Related, Ryoka Digital asked, Ryoka, it's just kind of like a brand.
Yes, okay,
yeah. It's just someone with an avatar. How do you think quantum theory will shape technology in the future?
That's a very good question. Of course, it's already shaped technology completely in the present.
It's ongoing, yeah.
Yeah, no, I mean, all the electronics in the world is all based on quantum mechanics. But it's particularly simple quantum mechanics of a small number of electrons and things like that. The quantum mechanics that we're exploring now is the quantum mechanics of massive entanglement. Large number of qubits, those are quantum bits, which are massively entangled with each other, and how that can be used to do things that no classical computer can do. I can't tell for sure how it's going. Quantum computers will probably be built. They will be built to try to exploit this massive idea of entanglement. What problems will it solve is unclear. It conceivably could be that people will build quantum computers and not figure out what to be able to do with them. Now, I don't think that will happen. There's one thing that you can do with a quantum computer, and that's to simulate quantum systems in a way that classical computers couldn't. Classical computers can never be built big enough to explore more than probably 100 qubits. 100 qubits doesn't seem like very much. No classical computer can do the calculation of following what 100 qubits do. So if you're interested in some quantum mechanical system and you want to study it, the most efficient way to study it is not to program it for a classical computer. That will never go very far, but to program it on a quantum computer, and then you have a good chance to be able to explore it. So that's a scientific purpose for it. You want to understand how certain chemical molecules behave, the big chemical molecules which are too big to do on a classical computer. You run it on a quantum computer. You want to understand new materials, quantum mechanics, materials that depend for their properties on quantum mechanics. Classical computer, for the most part, can't do it. You'll be able to simulate it on quantum computers. Will they be able to solve problems that are the usual kinds of problems that you hope computers can solve? That remains to be seen.
Mm-hmm. The last thing I was wondering is now, so you're both an accomplished physicist, but you're also a physics educator.
Okay, I hope so.
For better or worse, right? All of your videos, your books. You clearly have a knack for communicating these ideas.
That's nice to hear.
At least it works for me.
Yeah.
If you could impart any particular ideas across the population about physics and an understanding, what would they be?
I don't really know. Let me answer a totally different question. Why did I start teaching for the public?
Sure.
I think the simple answer is that it was fun. I like teaching. I get two things out of teaching. I like to perform. In that sense, I have a bit of Feynman in me.
Mm-hmm.
And I get a kick out of performing. That's one thing. There's another element to it. I find that the process of figuring out how to explain things is very, very helpful in formulating new ideas. To me, teaching is absolutely essential for doing physics. Much of my physics began with trying to figure out how to explain something. It almost doesn't matter whether it's explaining to another physicist or explaining to a layperson. In particular, I found that trying to explain things to a layperson, I explain them honestly, explain them not through fake analogies, but to try to give an honest and clear explanation of something, often really focused my ideas on how the thing works. And so it has value to me that was above and beyond just the fun of teaching. And I did find that teaching for the public, Stanford's continuing studies, was especially valuable this way. The students, they were anywhere between 50 years old and 95. That was actually true. There was a 95-year-old lady she followed. She knew what she was doing.
Yeah.
So I found that their curiosity, they had some degree of technical background. They tended to know a bit of mathematics, just a bit, through calculus. And they were very curious about physics. I found teaching them to be especially gratifying. And I really would spend a lot of time figuring out how to explain hard things to them. In the process, I often found out I understood them so much better. So that was why I got into teaching in the public, called the public sector or whatever. Mm-hmm. I don't know that there's any particular thing that I would want to convey to them. There's some obvious answers. You want to convey to them that science makes sense. You want to convey to them that scientists aren't phonies, that they really do sometimes know the answers to things, that there are facts and so forth.
Yeah.
Of course, all these things are true. Was I motivated by that? Not really. I was just motivated by having fun and enjoying teaching. I think there was one more thing. My father had a bunch of friends. They were plumbers, and they were funny characters. They were sort of intellectuals, but none of them had been past the 5th grade. They were very curious about all sorts of things, some science, some history and stuff. And they were mildly crackpotty.
Mm-hmm.
Why were they crackpotty? They were crackpotty not because they were intrinsically crackpots. They were crackpotty because they had no venue in which they could find out what was real science from fake science. They were plumbers. They couldn't go ask some physicist, is this real or is that not real?
Mm-hmm.
And I always felt some sense that I would have liked to be able to go back in time to my father and his friends and tell them what was real and what was fakey stuff.
Yeah.
I always, that, I don't know, emotionally, I think that sort of did come into the reason why I liked teaching these people. They reminded me of,
yeah.
Yeah.
That's great. Well, thank you so much for your time.
Okay. It was good.